So here we're going to look at muscle basics explained. So when you're trying to open that pickle jar and you feel the strain on the muscles, you get an appreciation for what's actually going on. So we have myofibrils, which are why striations are seen. So if we look at this kind of image here of the muscle, you notice we have myofibrils. They're densely packed rod-like contractile elements called myocytes. So here we see these kind of like fibers, like a bundle of fibers all together. They make up the vast majority of the muscle volume. You also notice within these myofibrils, they're perfectly aligned within the fiber. They're all nicely organized, and they create repeating series of dark A bands and light I bands. So how you can try to remember that is the I band, and the second letter is I in light, and the second letter in dark is A, and that's that kind of A band. So dark A bands and light I bands, as we see here. And we see nuclei kind of oriented around here. Now, within this, we have the sarcomeres and the banding patterns. So now we're looking at one specific kind of fiber, if you will, here. They're composed of thin filaments that do not overlap thick filaments in the lighter H zone. So we have these kind of like overlapping here. So here we go into the sarcomeres and the banding pattern. We have thin filaments that do not overlap thick filaments in the lighter H zone. We have these M lines that appear darker due to the presence of desmin. So we're looking at kind of our sarcomere here. We have kind of all of these kind of like lines in these thick and these thin filaments, and they kind of like are right next to one another. They're not kind of like they're not on top of one another. They're kind of like all in the spaces there. These are the smallest contractile units of the muscle in the region of the myofibril between two successive Z discs or Z lines here, as we can kind of see this kind of section here within these muscle fibers. The regular organization of these sarcomeres gives skeletal and cardiac muscles their distinctive striated appearance. And they're composed of those myofilaments made of those contractile proteins, and those filaments are composed of the thick myosin and thin actin filaments. We see here the thin is represented by the blue and the thick by the red lines here. The sarcomere and sliding filament model of contraction. So what's going on here? Well, because they're not directly overlapping, because they're like right on top of one another, what they're doing is they're kind of sliding across. So we kind of use the cuffs of my arms here, and we kind of have a space between them. We start here, and then they'll get closer. And that's what's happening in this sliding filament theory. During the contraction of muscles, the myosin retracts along the actin myofilaments, compressing the I and the H bands together. During the stretching, this tension is released and the I and A bands expand. The A band remains consistent throughout the length of the myosin myofilaments, does not change. It's like the length of my arms and hands don't change, but they're simply sliding. They're simply reducing the area or the distance between the ends there. This is this contraction that's occurring. We see that here, the relaxed form, where you have that large space in the H band, and then the contracted where they're sliding over one another, reducing that H band spacing. The myofilaments, we have a banding pattern. We have thick filaments extend the entire length of the A band. We have thin filaments that extend across the I band and partway through the A band. Those Z discs are coin-shaped sheets of proteins, and they anchor the thin filaments and connect the myofibrils to one another. So you have these anchor points, which allow when something contracts to help pull it together, because if they just slid all over the place, there'd be no contraction. Those two fibers are sliding across, and that's pulling in the ends there, condensing the total length and causing that contraction to occur in muscles. And we have tendons and ligaments. Tendons are flexible but elastic cords that are strong fibrous collagen tissue. And the key part with a tendon is it attaches muscle to bone. An example would be hamstring or quadricep. Tendons attach muscle, so we see here, directly to bone. Ligaments are also short bands, tough, flexible, fibrous connective tissue, but they connect two bones to cartilage or holds a joint together. The ACL is a prime example of here, and they're basically connecting two bones together, or two cartilage points as well. So again, tendon is a muscle to a bone, a ligament is linking two bones together. Now, how muscles work in a general sense. Muscles are attached to bones by straps of connective tissue called those tendons. Bones pivot about flexible joints and pulled back and forth by those attached muscles. You go through and start moving things around. Muscles only pull, they never push. So there's an antagonist that allows for movements in the opposite direction. So for example, if I move this way, right, we have muscles here that are being pulled. These are relaxing. But as I move my hand back up, the muscles on the back of my hand, those would be the ones that are contracting and shortening. So whenever a muscle or a group of muscles does, another muscle or group undoes that same movement. And we kind of see that here as you're running and moving your leg. Muscles, remember, are only pulling, they're never pushing. So how muscles work? Well, there's an origin, which is the muscle end attached to a tendon or stationary bone. We need something to pull against. Then there's the insertion, which is the attachment to that bone and contractile muscle. This antagonist is the muscles of a movable joint is attached to the opposing pairs. We have our flexors and extenders. We can kind of see a great example here of the hamstring. When that contracts, that's pulling the leg back. And we have the extenders here, the quadricep. When that gets pulled, that's pulling the leg or the foot here forward. We see a prime example of that here of soccer. We're going through and playing that as well. And we can see this in motion right here, where we have when the arm is coming up, we have these muscles contracting. When the arm is going down, these are relaxing, but these are doing the contraction here as well. There's two types of muscle contraction. There's isotonic and isometric. Isotonic is when the muscle actually shortens, thus moving the bones. That's the example that I've given you here. But we also have something called isometric, where the muscle does not shorten but exerts a force. The best way I can kind of give this an example is if you've ever picked up with your arms being straight a 5-gallon pail of water that's very heavy, you can feel your muscles working even though they're not contracting, or even though you're not maybe picking them up and lifting them. Just keeping your muscles straight can also have a force upon that, be an isometric form of contraction. Normal and atrophied muscles, so muscle mass is reduced as muscle atrophies with disuse, although atrophy due to disuse can often be reversed with exercise. Muscle atrophy with age, referred to as sarcopenia, is irreversible. So this is why if you have a muscle in a cast, for example, for an extended period of time that isn't moving, it'll atrophy and get smaller, but hopefully you can bounce back from that. If it's a short period of time and you're youthful, you can get that muscle back through normal use over time with physical therapy back to its normal mass. Muscle metabolism, energy and contraction. Well, with respiration, it's releasing energy from the sugar to make ATP. We have two pathways, aerobic and anaerobic, basically using oxygen and not using oxygen. Aerobic is a preferred method because it produces a great amount of ATP that your muscles need. However, when oxygen gets low, it sets a workout. Lactic acid and fermentation pathways can be used and be favored to generate some ATP. However, it's important to note that when your body uses ATP, protons are being produced, resulting in an acidic environment, and this is what's causing muscle burn. A lot of people misdiagnose it as being the lactic acid because they hear the term acid that's causing the muscle burn, but in this case, it's just the release of hydrogen ions, protons, an example, from ATP. Lactic acid is slowly converted to pyruvate in the liver, and it can actually help speed the process of reducing the amount of burn that you may have or feeling in your muscles. When you kind of get the eye twitch, you may wonder, your muscle contraction. It's kind of an example. Why is your eye twitch? Let's get a little YouTube video link there, but mainly it's caused from stress or limited sleep or high caffeine consumption can help increase the odds of that little muscle twitch. Lastly, dark meat versus white meat. White meat is fast twitch muscles, fibers, short energy bursts, and they tire a lot quicker. They have lower fat content and slightly higher in protein content. For example, the turkey breast would be an example of that. Dark meat is slower twitch muscles. They have long periods. They have high oxygen content and high myoglobin content, and also higher fat content. But its mono and polyunsaturated fats are slightly higher in cholesterol, and those will be found in your turkey legs, wings, and thighs. So if you're having Thanksgiving dinner and you like white meat versus dark meat, this is a great kind of example of exactly why there's different meat within the same, in this case, turkey, because they serve different purposes.